Okay, now we're going to describe some of the properties that these relations, and in fact relations in general, can have, and then we'll use these after we go through these examples. We'll use these to do some further analysis, looking at equivalence relations, preference relations, utility representations, and so on. So let's start in by just going through systematically several important properties that relations may have. So the first one here is that a relation is reflexive if for every element of the domain of the relation, every element of X, we have X is related to itself, reflexive. And so let's go through each of our examples and see which ones are reflexive. Well, of course, this one here is reflexive. So let's say that's reflexive. Here I'm using, this is R, the name of the relation. In gold, I'm using pink now to identify the properties the relations have. So R for reflexive. Here we have this relation here is really the same as the relation up here. The only difference is here I used F for the name of the function, and here I used U for the name of the function. And of course, the label or name I used for the relation was I, or this tilde here, and here I used R, but they're the same relation. So this is reflexive. And of course, this is reflexive because every element has U of X greater than or equal to U of X. So this is reflexive. This is clearly not reflexive. No number is bigger than itself. This is reflexive, of course. And this is reflexive because every number is greater than or equal to itself. Here we have a set of people. Living next door to someone is not reflexive. One doesn't live next door to oneself, so that's not reflexive. Living on the same block, I live on the same block as myself, so that would be reflexive. Being a sister to someone, not reflexive. I'm not a sister to myself, or one is not a sister to oneself. Daughter, similarly not reflexive. Ancestor, similarly not reflexive. One is not an ancestor of oneself. Let's go to our next property, and that is the symmetric property. A relation is symmetric if whenever we have X related to X prime has to be related to X as well. And of course, we saw that over here. Our first example here was symmetric because here we said that for every X and X prime, if X is R related to X prime, then X prime is related to X. That's symmetry. So the relation is symmetric. So all of these refer, maybe I should just put this up here, they all refer to this same relation. A, B, and C are not different relations. So that's a little confusing if I do that. Here we have three different relations identified here. And so the first one is not symmetric because if U of X is bigger than U of X prime, the reverse is not true. Or to say it in terms of preferences, if X is strictly preferred to X prime isn't going to be strictly preferred to X. So that's not symmetric. The next one is, of course, symmetric. It's the same as the one up here. And of course, this relation here is not symmetric because I could have X larger than X, U of X larger, strictly larger than U of X prime. And so X prime would be true, or X preferred or indifferent to X prime would be true. But if X is strictly preferred to X prime, if U of X is bigger than U of X prime, the reverse would not be true. So this is not symmetric. This is clearly not symmetric. This is symmetric, of course. And this, unlike this one here, this actually, no, this is not symmetric either, because if x is greater than x prime, this would be true, but x prime wouldn't be greater than or equal to x, so this is not symmetric. Living next door to someone, that would be symmetric. If I live next door to you, you live next door to me. So that's symmetric. Living on the same block, clearly symmetric. If I live on the same block as you, then you live on the same block as me. Being a sister to someone, well, is that symmetric? Well, if all of the people in capital X are female, then being a sister to someone in X would be symmetric. If my daughter has a sister, then that daughter is also a sister of hers. So this would be symmetric, but it would only be symmetric if everyone in X is female, because if we have any males, then X could be a sister to Y, but X could be female, Y could be male, and Y wouldn't be a sister to X. Y would be a brother to X. So this is not symmetric unless everybody in X is female. Daughter, clearly not symmetric, and ancestor, clearly not symmetric. Our next property is transitivity, transitive property. If we have X related to X prime and X prime related to X double prime, transitivity says that X has to be related to X double prime, exactly the property we have here. So maybe we should add here that this is the property of reflexivity, this is the property of symmetry, and this is the property of transitivity. So this relation is reflexive, symmetric, and transitive. This is the same thing, so this is reflexive, symmetric, and transitive. This is clearly transitive. If u of x is greater than or equal to u of x prime, and u of x prime is greater than or equal to u of x double prime, then u of x is greater than or equal to u of x double prime. So this is transitive. Similarly, this is transitive, and this is transitive. This is transitive. This one is transitive. What about living next door to someone? If I live next door to Joe, and Joe lives next door to Steve, I don't necessarily, in fact, in general, I don't live next door to Steve. So this is not transitive. How about living on the same block? If I live on the same block as Joe, Joe lives on the same block as Steve, then I live on the same block as Steve. So this is transitive. What about being a sister? Again, this would not be transitive, because Amy could be a sister to Bev, and Bev a sister to Amy, but Amy would not be a sister to herself. So this is not transitive. Being a daughter, that's not transitive. If Amy is the mother of Bev, then Bev is a daughter of Amy. Carol could be a daughter of Bev, but Carol wouldn't be a daughter of Amy, she'd be a granddaughter. So this is not transitive. Being an ancestor, what about being an ancestor? That one is transitive. My grandfather is an ancestor of my father is an ancestor of me, and my grandfather is an ancestor of me. So that one's transitive. Our next property is the completeness property. So we say that a relation is complete if for any two elements of x, x and x prime, either x is related to x prime or x prime is related to x, or of course possibly in both directions. So from here on in, actually, I'm not going to go through every one of these, but I'll just indicate which of the relations has the property that we're looking at. So here for completeness, which are the complete relations? I believe the only complete relations here are, well, let's first of all notice this relation here, where we have clearly for any two real numbers x and x prime, either x is greater than or equal to x prime or vice versa. So this is complete. And for the same reason, this is complete, because here the relation is defined in terms of the real numbers like this, which are the values of the utility function u. So here, this relation would be complete because for any two elements of x, any two alternatives, either u of x is greater than or equal to u of x prime or the reverse. And so since the definitions here are in terms of the relation between u of x and u of x prime, that says that this relation, whether we use this notation or this one, this is complete. And I believe those are the only two relations here that are complete. Down here, you could make up special cases with special limited sets X where these might be complete, but in general, these wouldn't be complete. Our next property is asymmetry. We say that a relation's asymmetric if this implication here holds for every pair of elements x and x prime, but you'll notice there's a new symbol here. So that's because what we want to say here is that the relation's asymmetric if it's always the case that if x is related to x prime, then x prime cannot be related to x. In other words, x prime x is not in the relation. So we're saying here then that x prime x is not in the relation R. That's the consequent of this implication. But of course, these relations are just subsets of x cross x, or x cross y more generally. And so since this is a set, a subset, we can talk about its complement, and its complement would be in fact, let me write this a little differently here. Let's say this is x prime x in R, but to say that x prime x that is not in R is to say that x prime x is in the complement of R. And I like to use R super C as a notation for the complement. This is one concept, the complement of a set, where lots of different notations are used. Lots of different people use different notations. This is one that I like, but in this context, I actually prefer a different symbol, and that is the R with a slash through it. So instead of R super C, I'm going to use R with a slash through it. So this is the complement of the relation R, or the set R. So this says x prime x is in the complement, which is the same as x prime x is not in R. And so that's what the consequent in our definition of asymmetry is saying. And so which are the relations over here that are asymmetric? Well, first of all, notice that a relation cannot be both symmetric and asymmetric. So any relation that's symmetric, not going to be asymmetric. This relation here is asymmetric, and I'll use A to indicate that. This is asymmetric. This relation here is asymmetric. You'll notice that if x prime is bigger than x, x can't be bigger than x prime, and for the same reason, this is asymmetric. And I believe the only other relations here that are asymmetric are the daughter relation, which is clearly asymmetric. If x is a daughter of y, y can't be a daughter of x. So this is asymmetric. And similarly, ancestor is asymmetric for the same reason. And our next property of relations is the antisymmetry property. Sounds like it's the same as asymmetry, but it's actually, there are two different words we use to mean two slightly different ideas. So a relation's antisymmetric if having x prime r x and x r x prime means it has to be the case that we're talking about only one element, and that's x prime equals x. You could say this in the contrapositive by saying if x prime is not equal to x, that is, if we have two distinct elements, it can't be the case that both x prime rx and x rx prime, they can't both happen. So then it's clear that an asymmetric relation is antisymmetric. And I say it's clear, and why is that? That's because if a relation is asymmetric, then the antecedent of the antisymmetry definition can't hold, can't be true. So the antecedent says x prime rx and x rx prime, and asymmetry says you can't have that. So that means that if we have an asymmetric relation, then vacuously it's antisymmetric, because the implication in the antisymmetry definition has to hold vacuously. So all of the asymmetric relations are also antisymmetric. Are there other antisymmetric? And so I'm going to use N for antisymmetric because I've already used A. So antisymmetric, 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 antisymmetric. There are two more relations here that are antisymmetric. Oddly enough, it seems paradoxical, the equality relation is antisymmetric. How can it be symmetric and antisymmetric? Well, it turns out that the equality relation on any set X is both symmetric and antisymmetric, and it is the only relation that can be both symmetric and antisymmetric. And it's antisymmetric because if x prime r x, that says x prime equals x. And if x r x prime, that says x equals x prime. So in order to have the antecedent hold, x prime already has to be equal to x. Let's make sure I said that right. X prime has to already be equal to x, so the consequence certainly holds. So in a certain trivial kind of sense, the equality relation on any set X is going to be both symmetric and antisymmetric. But the other place where this shows up here is actually important. You'll recall that when I introduced the relation here defined by utility functions, and the relation down here, the familiar greater than or equal to relation, and equals and greater than, I said that these two relations are clearly very similar to one another. They're very much alike, but I said they're not identical. And this is the way that they're not identical. Well, we've just said that this relation here is antisymmetric, but the corresponding relation here of indifference is not antisymmetric, because here we can indeed have two distinct alternatives to be chosen from amongst. We could have two distinct alternatives that the decision maker is indifferent between. He says they're both just as good as one another. So we could have two distinct elements that are indifferent to one another. The decision maker is indifferent between. And that can't happen with equality. We can't have two distinct elements that are equal to one another. And the same is true here for this relation and this relation. This relation is antisymmetric because if x prime is greater than or equal to x and x is greater than or equal to x prime, then x and x prime have to be equal, have to be the same element. So this is antisymmetric. But this is not. This is not antisymmetric. It's just the same distinction as here and here. That is, we could have two distinct elements, x and x prime, where x is at least as good as x prime and x prime is at least as good as x, but they're distinct because the decision maker is indifferent between them. But that can't happen down here. If x prime is greater than or equal to x and x is greater than or equal to x prime, then x has to be equal to x prime. So that's the distinction between this relation of preference defined from the values of a utility function on the one hand, and our familiar notion of order greater than or equal to on real numbers. So that, I believe, takes care of all of the relations that are antisymmetric. And finally, we have the notion of an irreflexive relation. And that simply says a relation is irreflexive if no element of X is R related to itself. And so which relations here are irreflexive? Well, clearly this is, well, let's go down here. This is irreflexive. I for irreflexive. And by the same token, this is irreflexive. And down here, the irreflexive relations would be everything except being on the same block. So this is irreflexive. And you can, of course, check these out for yourself. So I'm doing these quickly and not sort of going through the arguments, but you can check each of these and should check each of these for yourself to verify that each of these relations has the properties that we've laid out here, and that each relation doesn't have the properties that I haven't written. In other words, verify for yourself that each of the things I've written and that I haven't written is accurate for each one of these relations. That's a really good and important exercise. So I think that wraps up our introduction to binary relations. And so we will use what we've done here in subsequent lectures to talk about orders and pre-orders, preference orderings and utility representations of preference orderings. That's the foundations of utility theory, preference theory, theory of choice, consumer theory, and so on. And we will also use what we've done here to talk about equivalence relations and partitions, and we will apply those ideas to talk about information and how information is analyzed and used in economics and game theory. So that wraps things up for today. See you all next time.